Swayam Prabha. Digital India. Educated India.
Welcome back, my dear friends. A very good morning, good afternoon and good evening to all the participants and the students. And this is the TQM2 lecture under the NPTEL MOOC series, and this is the 32nd lecture. That means we are in the almost at the fag end of this course, because as you know, this is each day is a half an hour or 30 minutes lecture for 5 days in a week, and that is 20 hours. So, it is 40 lectures. So, we are in the last week, and I am Raghunandan Sengupta from the IME department, IIT Kanpur. So, if you remember the last class, which was the 31st one, we did start actually the concept of 3 factor models, fractional factorial models. That means basically trying to find out the overall combination of 3 to the power k. And I did mention about this initially when we are doing the 2 to the power k factor with levels of dependence being on the third order or fourth order or fifth order. Those are the subscripts which you are giving. So, I will come to that once more. Now, we are doing the frothing of the syrup, and there was nozzle dimensions or the diameter or the overall area of the nozzle was important, pressure was important, and the temperature was important. So, all these factors are important. So, based on this we were basically studying the problem. So, next we observe the response surface contour plots of constant syrup loss. So, frothing was basically there was loss. So, and now we want to find it out as a pressure, speed and pressure. Okay, my apologies, it was basically pressure and speed of each nozzle, and obviously nozzle diameter would be fixed later on after the speed and pressure are adjusted. Obviously, it will mean that you want to basically adjust the pressure, adjust the speed, and then finally decide on the nozzle dimension, because once nozzle dimension is fixed, it cannot be changed, because the manufacturing process you have to order it, there is cost for that, and all these things are there. So, these counter plots reveal the considerable useful information about the performance of this filling system. Because the objective is to minimize syrup loss, nozzle type 3 would be preferred. So, they were basically 3 levels 1, 2, 3, pressure was at 3 levels, could be general, and then speed could be at 3 levels and so on and so forth. That is why it was 3 to the power k. So, continuing reading it, because the objective is to minimize syrup loss due to frothing, nozzle type 3 would be preferred, as the smallest observed counters of -60 appear only in this plot, and they can be analyzed accordingly. Filling speed near the middle level of 120 revolutions per minute or RPM, and either low or high pressure levels should be used in order to basically minimize the frothing or the syrup loss. So, the counters of the constant syrup loss units are given in cc cubic centimeters of -70 as a function of speed and pressure for nozzle of type 1, 2, 3. So, if you see the diagrams here, so this was basically a nozzle of type 1 or a certain dimension, this is a nozzle type 2 of a certain dimension, and this was a nozzle of type 3 of certain dimension, and the contours basically were, you are plotting pressure and speed. So, let me highlight the pressure and speed once more. So, this was basically the pressure along the y axis, the speed, this is for nozzle 1 type 1 dimension, pressure along y axis, speed along x axis for nozzle of type 2 dimension, this was pressure and speed for nozzle of type 3 dimension. Now, from this we will go into analyzing the overall importance of this. So, basically it is giving you a plot of how the pressure and speed change for one dimension. So, in case if you see look here, I will just, so considering that the pressure is slowly increasing, the nozzle speed also varies, then after reaching a peak it starts decreasing. So, they would be different, and this is for the dimensions being 20. So, obviously you have dimensions of 60, 40. So, 20 would basically mean this is the counter plots of the overall fluctuation of speed and pressure for a type of nozzle which you are trying to utilize. When constructing counter plots for an experiment that has a mixture of quantitative as well as qualitative factors or variables or attributes, it is not unusual to find that the shape of the surfaces of the quantitative factors are very different at each level of qualitative factors. So, obviously qualitative and quantitative interrelationship would be such that trying to find out the counters would be quite interesting in this shape. This is noticeable to some degree in figures where the shape of the surface for nozzle type 2 is considerably elongated in comparison to the surface for nozzle type 1 and type 2, because in there the combination in nozzle type 2 the overall counter is much more elongated or in one direction is basically stretched. When this occurs, it implies that there are interaction present between the quantitative and qualitative factors, and as a result the optimum operating conditions and other important conclusions in terms of the quantitative factors are very different at each level of qualitative factors combinations. The numerical partition of ABC interaction into its 4 orthogonal 2 degrees of freedom components using the data of 9.1, which is basically speed, pressure, and trying to find out a nozzle dimension, and then trying to basically find out the frothing and the loss of syrup. First, select any 2 of the 3 factors. So, basically we have pressure, speed and nozzle dimension. The 3 factors C, A and B you consider and compute basically the values of I and J, and I and J, if you remember, over the combined effects which were happening and how you could find it out. It could be A B square, C A B C square, and so on and so forth combinations. So, compute I and J, that is the total of the A B interaction at each level of the third factor of C. So, you are basically have you plot the values of C along the leftmost column. So, these are basically 10, 15 and 20. So, these are basically the dimensions which we are talking about, and the values of A and B. So, which was corresponding to the fact they were the speed and the pressure. So, the factor B, so I should use a different color. So, it will be, so this is for B, and the values are, I will just highlight them. This basically starts from 100, goes on to 140. The combinations are given. So, for 10, for a nozzle dimension of 10, you have 10, 100, 120, 140. Then for dimensions of 50, you have again the combinations of 100, 120, 140, and finally for a nozzle dimension of 20, the combinations are 10, 100, 120, 140, and for similarly for basically for A, the values are given as 1, 2, 3, and based on that you find out the total combinations and all the values are coming. So, I will use another color. So, the values are given starting from the first row minus 60, 41, 74 to the last row which is basically 67, minus 51, 58. So, these are the combination of the values which you are getting. The totals which you find out for the values of I and J corresponding the combinations of A, B, C which you have. If you remember, I, J were in different variables as A, B square, C, A, B, C square, and so on and so forth. So, the values are given the second last and the last column. So, the second last I values are given. Again, I should use a different color. Let me use the light, yes. So, these are the values of I, and these are the values of J. Based on that, you can do the calculations accordingly. The I, which is the combinations of A, B in different factors, and J, which is also combinations of A, B in different factors. Totals are now arranged in two-way table with factor C, and the I and J diagonal totals of these new displays are computed as follows. So, we basically plot only the values of I, J and C and try to find out the combinations in such a way, so that we are able to get the maximum effect accordingly. The INJ diagonal total computed above are actually the totals representing the quantities, which are, if you remember, I was mentioning time and again that INJ can be in different combinations. So, I is basically A B square C, and J is basically given by A B C square, and based on that and on the other combinations I could be A B C square. So, J was here the combinations A B C, which are basically, if you remember, we are denoted as W, X, Y and Z components. The sum of the squares. So, obviously, the main effect we want to find out is all the variables on the leftmost set of columns. Then you basically have the sum of squares, and also the second last row would be the errors. Besides that, the total of all the effects, all the factors A, B, C and all the combinations of A, B, C, and summed up with the sum of the errors would basically give you the total sum, and based on that you have the degrees of freedom. So, the sum of the squares, or the squares divided by the errors squares divided by the degrees of freedom would give you the F factor, and F factor based on whether it was the left hand test or the right hand test, and also the concept of the p values, and whether you want to basically subscribe to the fact whether you want to consider that H naught as true or untrue, you will basically take a decision accordingly. So, although this is an orthogonal partitioning of the SS sum of the squares of ABC combinations, we point out again that is not customarily displayed in the analysis of table value table. So, and you have basically ANOVA and MANOVA. In subsequent sections, we discuss the occasional need for the completion of one or more of the components, and basically try to find out how this effect can be maximized. Effect means that overall effect you want to find out for trying to predict the overall effect from the factors, in order to predict what is the decision or what is the so called the y value, which is the dependent variable which we have. So, now the general 3 to the power k design. So, 3 are the levels of each factors which are there. So, the concept utilized in 3 square and 3 cube. So, obviously, I am trying to utilize the nomenclature we also always use, which basically 3 to the power 2 and 3 to the power 3. Design can be readily extended to the case of k factors also. So, it can be 3 to the power k factors also, each at 3 levels. So, basically there are k factors, it can be a 3 level. So, it will be 3 to the power k. If there are 4 factors, each are at k level, it will be 4 to the power k, and so on and so forth, but obviously the degrees of freedom will be calculated accordingly. The usual digital notation is employed for the treatment combination. So, that 0, 1, 2, 0 represents a treatment combination of 3 to the power 4 designs depending on the different combinations which we have, with A and D at the lowest level. So, if you find out this, so this is basically what you have a 0, 1, 2, 0, they are. So, this is for A, this is for B, this is for C, this is for D. So, if there are 3 levels, A is at the and the levels are 0, 1, 2, or say for example, -1, 0, 1. So, consider this -1, 0 and 1. So, A is at 0 level, which is at the normal level, and okay. So, let me change it, my apologies, it would be basically be 1, 2, 3 levels. So, if it is 0 level, A would be at the minimum level. If B is at 1, it is the normal level average. C is at 2, is basically at the high level, at the highest effect which you can find out for C, and the value of D, it is basically 0, means it is the lowest level. So, in case say for example, you have the factors are A, B, C, D, and the levels are 3, and the overall effects can be basically given so called weights. Let me use the words weights. So, they are a -1, 0, 1. So, obviously, A would be, if it A is -1, it is the lowest level, B is basically at 0, it is at middle level or normal level, C is basically as +1, it is at the highest level, and D is basically again +1 is the highest level. So, the nomenclature how we use, we will basically assign them accordingly, but again I am repeating which I did mention the example, if you remember, of the building the dam, or the example of electrical circuit, or the concept that we want the average to be 0, but we also want the variance to mean variance. So, both of them have to basically met. It is basically something to do with, may not be exact, the concept of unbiasedness and consistency. The usual digital notation is employed for the treatment combination. So, 0, 1, 2, 0 represents a treatment combination of 3 to the power 4 combinations, where A and D are the lowest level, B is the intermediate level, and C is the highest level, as I mentioned 0, 1, 2, 3, where the levels are basically given as 0, 1, 2. So, there are 3 into k treatment combinations with 3 to the power k minus 1 degrees of freedom between them. So, these treatment combinations allow sum of squares to be determined for the k main fx, each with 2 degrees of freedom. So, obviously, it will be k 2 factor interactions each with 4 degrees and 1 factor interaction with 2 to the power k degrees of freedom, depending on the number of factors which you have. In general, h factor interaction. So, if it will be 2 to the power k, for if at 2 levels, if there are n replicates, then obviously it will be n multiplied by 3 to the power k minus 1, it will give you the total degrees of freedom, or the degrees of freedom for the errors would be 3 k into n minus 1. So, obviously, the sum of the degrees of freedom would basically give you the overall information as the sum of the squares of all the factors errors plus the error of the sum of the so called sum of the squares of the errors of the white noise, that being added to the sum of the square of the errors of the variables should basically give you the total errors. The size of the design increases rapidly with k. So, as k is increasing, obviously, it becomes 2 to the power k, then it becomes so if it is increasing. So, if it is 2 to the power k, and if there are 2 factors, it is 2 to the power 2 4. If it is 2 to the power 3, it is 8. If it is 2 to the power 4, it is basically 16. So, it basically increases at a very high rate. And if it is 3 or 4 or 5 different levels for each factor, so obviously the increase is much faster, like 5 to the power 2, 5 to the power 3, 5 to the power 4. So, obviously 5 square would be 25, 5 to the power 3 would be 125, and it increases accordingly. So, if it is 25 into 25, it will be 625 different combinations you have to find out. So, obviously it is tedious, but you have to make a decision that what is the best level of efficiency considering the time constraint, which would also mean that there is a cost for doing all this work. Confounding of the TK factorial design, fractional factorial design problems. Even when a single replicate of 3 to the power k design is considered, the design requires so many runs that it is unlikely that all 3k runs can be made under uniform conditions. This confounding in blocks is often necessary. Thus, the 3k design may be confounded in a 3p incomplete blocks such that p is less than k. So, if our overall set of information based which we are trying to find out the overall effect, it can be done by p such factors where p is less than k. So, obviously, it should be attempted. Thus, this design may be confounded in 3 blocks, 9 blocks, so on and so forth, depending on the overall grouping you want to do. The 3k factorial design in 3 blocks. So, we wish to compound the 3k design in 3 incomplete blocks. So, block 1, block 2, block 3, but they would be done in such a way that the values of factor p is less than k. These 3 blocks have 2 degrees of freedom among themselves. Thus, they may be 2 degrees of freedom confounded with the blocks, because there are 3. So, obviously, the overall effect would be 2, or degrees of freedom would be 2, the fx. The 3k factorial series, in this series each main effect has 2 degrees of freedom. Furthermore, every 2 factor interaction has 4 degrees of freedom and can be decomposed into 2 components of interaction, basically AB square, or it could have been by a square b also, depending on how you are trying to find out the overall effect. So, each with 2 degrees of freedom, every 3 factor interaction has 8 degrees of freedom and can be decomposed into 4 components. So, the 4 components are basically AB C square, AB square C. So, obviously, if we are able to basically define ABC accordingly, it could have been by given as a combinations of A square, B, C, or different combinations as required. And obviously, you would basically have the last one is AB square C square, each with 2 degrees of freedom. So, it will be 2 degrees freedom for any combinations as we find out. And as there are the number of blocks increases or number of factors increases, the combinations would basically also increase accordingly. It is thus convenient to confound a component of interaction with the blocks and do the calculations accordingly. So, the general procedure is to construct a defining constant. So, with alpha I represents the exponent in the ith factor in the effect to be compounded, and xi is the level of the ith factor in a particular treatment combinations. Thus, for the 2 3 to the power k series, we would basically have alpha I is basically the factors would decide the what is the level of importance we are going to give. So, in alpha I is equal to 0. So, where I is basically 1 or 2 with the first non-zero alpha I become unity, and the lower levels would obviously be eliminated by considering the factors as 0. So, or so obviously, if 3 or 4 or 5 or 6 are considered. So, obviously, technically the lower values would be we cannot consider. The treatment combinations in the 3 to the power k designed and assigned to blocks based on the value of L. So, obviously, it would be a mod 3 depending on 3 factors, mod 4 depending if there are 4 type factors, mod 5 depending on 5 factors, and so on and so forth. Because L, which is a mod 3, can take only on the values of 0, 1, 2, it is higher, it is 0, 1, 2, 3, and corresponding to that it will increase. So, these 3 blocks are uniquely defined. Once they are uniquely defined, you can find out the combinations accordingly. The treatment combination satisfying L is equal to 0 constitute the principal block. The block will always consider the treatment as at their lowest level 0, 0, 0, 0, 0, and then different combinations of 0, 1, 0, 0 or 0, 0, 1, 0, 0. So, I am basically repeating it zeros depending on how many such different factors which you have. We can find out the best possible combinations of the factors to give you the maximum output. Output obviously, whenever I use the word output, it basically means I am able to predict it to the maximum level, such that the white noise or the sum of the squares of the errors is as low as possible, such that our prediction is the highest of the highest accuracy. Suppose we wish to construct a 3 to the power 2 factorial design in 3 blocks. Either component of the AB interactions are AB or AB square, or it can be A square B, may be confounded with these blocks. So, arbitrarily choose AB square, it could have been A square B is also. So, the combinations are x 1 into 2 x 2, and basically the factors could be 2 x 1 plus x 2 also, depending on the combinations we are going to take. The value of L, which is of and now we are considering mod 3 of each treatment combinations, can be as follows. So, once we find out, it could be 0 0, that means at their lowest level, 0 1 they can be at the first one is the lowest level, second one is the middle level, it can be it can be 0 2, first as the lowest level, so the second one as the highest level, the combination can be 1 0, that means the first one as the middle level, second one at the lowest level, it could be 1 1 where both of them are the middle level, it can be 1 2 where the first one is at middle level, second one is the highest level, and the combinations could continue. So, if it is 2 0, the last one which you see, it will gives you the level of interaction for factor A as high, at like if there are 3 levels is the highest one, and the effect of B which is at 0 it is as the lowest level, because we are considering 0 1 2 as the combinations. So, 3 square design in 3 blocks with AB square confounded. So, we basically consider 3 blocks. So, the block 1, so let me highlight block 1, block 2 and block 3. The combinations, if you see, it is 0 0 which is low low, 1 1 which is basically middle middle or normal normal, 2 2 is high high. Basically, there are 2 combinations which I am considering. So, these 3 are basically the blocks, and there are 2 factors. So, that 2 combinations is coming out here. If there are 3 factors, it could basically would have been 0 1 0, 0 1 1, 1 1 1 and so on and so forth. So, this value of 1 1 0 2 1 0 2 basically gives the combination where the first one consecutively or respectively are middle value, where my highlighter is being highlighted, the pointer, high value and low value. For the second factor, it will be 0 1 2 which is low value, middle value and high value, and for block 3 which you are considering is 0 1 1 2 and 2 0. So, it will be for the first factors it will be low, middle, high, and for factor 2 it will be middle, high, low. So, the combinations if you take a geometric view, obviously there are 2 factors also, as I mentioned. Along the x axis you have basically you take factor A as it is given, it could have been factor B also. Along the horizontal, the vertical line you take the other factor, and the grid structure which you have here in the Cartesian coordinate gives you the different combinations. So, the combinations points are, if you notice down 0 0 is there. So, which is belongs to block. Okay. By the way, we are trying to basically mark this colors of the dots in the same way, so denoting in which block they belong. So, if you consider the diagonal one going towards the right hand corner on my right, basically 0 0 1 1 and 2 2 are in block 1, corresponding to block 2 you have basically 1 0, then you have basically 0 2 1 and basically you have 0 2. So, these are for block 2. I am just using the red color. Then if I use 0 0 1 1 2 2 is basically in block 1. So, if you consider here, and the red one basically for BB block 2, block 3 would be 0 1 1 2 2 0. So, they are here. I am just trying to basically draw the arrows in order to basically depict in which combinations they can be done. It could have been done in other combinations also, the blocks 1 2 3, but this is just a sample set of the calculations we are trying to do. The elements in the principal block form a group which represents 2 addition modulus of mod 3. Referring to this diagram, we see that the combinations are basically 22 and 0 0, or which is basically high high and low low. Treatment combinations in the other 2 blocks may be generated by adding the modulus 3, and any element in the new block can be addition and subtraction can be done accordingly. So, generate block 3 would basically do the combinations accordingly. We illustrate the statistic analysis of the 3 square design confounded in 3 blocks by using the following data, which comes from the single replicate of 3 square design as shown in figure 9.6. So, the blocks are, as I mentioned, block 1 2 3, the combinations were 0 0 1 1 2 2 for block 1, block 2 was 1 0 2 1 0 2 and block 3 was 0 1 12 and 10. If you find out the block totals basically comes out to be, after finding on the blocks weights, comes out to be, for block 1 it is 4 minus 4 which is 0, for block 2 it is minus 2 1 and 8 which is 7, and block 3 it is again plus 5 and minus 5 it is 0. So, based on that we can give the importance accordingly. Using the conventional method for analysis of factorials, we find out SSA, which is the sum of the squares for A factors, SSB for sum of the square of the B factors, they are 133.56 and 0.22. So, if you consider the factors and the analysis of the variance of the data table are given. So, the blocks again I will only go to the final one which I am trying to highlight. On the leftmost column you have the sources of variations, which are blocks A, B, combination errors and the totals. The sum of the squares are given, the degrees of freedom are given, sum of the squares are given in the second last column, degrees of freedom in the last column. Based on that you can find out F, predict whether the p values are high and low, and basically pass your judgment accordingly. So, with this I will end the 32nd lecture and try to basically continue in more details about this in the 33rd and the few remaining lectures, and also wrap up the whole course accordingly. Have a nice day and thank you very much.